So, welcome back after a short break. In the example that we just went through, we learned several things, and let's list a few of them. The first thing is that the sample mean has a Gaussian distribution. Of course, we have not yet proved it theoretically, but we have seen it through simulations, and at least for the case of Gaussian distribution, and we have also seen that in the case of the samples falling out or the observations falling out of a uniform distribution, the sample mean still follows a Gaussian distribution, but there is a small catch there. If we look at the case of fewer observations, that is when n is small and the samples fall out of a non-Gaussian distribution, there is no need or necessity. In fact, the sample mean does not follow Gaussian distribution. It is only when the n becomes large, when the sample size becomes large, the sample mean tends to follow Gaussian distribution regardless of the distribution of the observations, and this is what is the essence of central limit theorem, as we will shortly review. That is the first point. The more important point that we have learned is the role of the distribution of the statistic in hypothesis testing. Of course, we have shown this only in the case of, not shown, I would say we have discussed this in the case of mean testing, but that is true of the general hypothesis test of the form theta equals theta naught, and that f of theta hat plays a critical role in hypothesis testing. The way we used f of theta hat is to look at the or to compute the probability of the test statistic taking on a certain value or within the interval of the observed value, and if that probability turns out to be quite low, lower than what we can accept, which we call as a critical value, then we reject the null hypothesis. So, as you can see, f of theta hat plays a critical role. And the other thing that we have seen is that there is going to be certain error in any hypothesis test because it is based on probability and a critical value that I set. That is where we end up with type 1 and type 2 errors, formal definitions of which we will give later on. So, now let us continue with our discussion on sampling distributions, where we will now try to derive theoretically the distributions of the statistics of interest, namely the sample mean, sample variance and so on. In this lecture, we will look at sample mean. In the next lecture, we will look at difference in sample means, sample variance, ratios of sample variance and sample proportion, ratios of or differences in sample proportion, and eventually when we talk of correlation, we will also look at distributions of sample correlation. In order to derive the theoretical results, some standard results that are available in the distribution theory can be invoked, and the first result is right in front of us, which says that the linear combination of Gaussian random variables or a weighted sum of Gaussian random variables is also Gaussian distribution. This is a result that we have seen earlier, it is not something new, but let us use this opportunity to revisit that. Y is a new random variable that has taken birth through a linear combination of n Gaussian random variables, and each random variable in the sum follows a Gaussian distribution and has the same mean and the same variance. So, that makes it easy to derive the mean, or you can actually assume that each random variable has a separate mean and separate variance. Even then you can derive, as I have shown here. The result that is shown here is for the general case. It is very easy to show these results. All you have to do is apply the expectation operator, that is compute expectation of y, and use the linearity property of the expectation operator and show that the mean of the resulting random variable y also adds up in the same proportion as y itself. And the other assumption, of course, that we are making here is that xi's are uncorrelated or independent, and we will we can recall the definition of uncorrelatedness or independence. Basically, that means there is no covariance between any pair of random variables in the summation. In which case, the variance of y simply turns out to be the weighting square in your sum times the sigma square I. So, let me just quickly elaborate that a bit more for you. So, in general, when I have a pair of when I am adding up, let us say, two random variables x1 plus x2 to produce, let us say, alpha 1 x1 plus alpha 2 x2 to produce a new random variable. Of course, as I said, it is straightforward to see that mu y is alpha 1 mu 1 plus alpha 2 mu 2. This is regardless of the distribution of x1 and x2, and regardless of whether x1 and x2 are uncorrelated, correlated, independent, dependent. It's got nothing to do with those requirements. When it comes to the variance of y, which is expectation of y minus mu y to this whole square, and once you plug in the values of the expression for y and expression for mu y, you would end up with this expression, which is alpha 1 square sigma square 1 plus alpha 2 square sigma 2 square plus a third term, which is 2 times covariance of x1 x2. And this is a generic expression once again. This has got nothing to do with x1 and x2 falling out of a Gaussian distribution and so on. So, in deriving these results, distribution has no role to play. Now, if you assume that x1 and x2 belong to a random sample, that is, they are independent, then by independence means uncorrelatedness, and therefore you can strike this off and you end up with this expression. And now you can extend this result to the general case of n observations. Now, coming to the distribution of y is what the other result states. That is where we are invoking the fact that each xi falls out of a Gaussian distribution with mean mu I and variance sigma square I. And the result says when I add up two such Gaussian random variables, then the resulting variable y also has a Gaussian distribution with this mean and this variance. So, it is something that we can straight away use for the sample mean as an illustration. Suppose in place of y I have x bar, and in place of alpha 1 and alpha 2 I have 1 over n, then we have x bar is 1 over n sigma I equals 1 to n xi. Xi of course is a random. At this stage we are using the notation that xi is a random variable. In practice what you would do is you would replace a random variable with the value that you have in the sample. Because we are now interested in the distribution of x bar, we are using the random variable notation. So, now we can straight away use this result if xi, each observation is falling out of a Gaussian distribution. And that is what we have essentially seen in the illustration in R, that x bar follows a Gaussian distribution. Of course, in the example that we illustrated, every observation fell out of the same Gaussian distribution, mean and sigma square. Specifically, we simulated for the case of mean 0 and variance 1. But this need not be true in general. And now you can figure out what is the mean of x bar using this result here. Expectation of x bar, so I will also use this uppercase notation so that we are looking at random variables. Expectation of x bar would be 1 over n times sigma expectation of xi. Since each xi falls out of the same distribution, I have 1 over n sigma mu I equals I running from 1 to n, and therefore expectation of x bar is mu. That means the average of x bar is the same as the average of x or xi, you can say. Now this is very important because this is a test for bias of the estimator. We say that any estimator is unbiased if its average is the same as the true mean. Here the estimator is sample mean, and bias is in general for any parameter theta, bias is defined as expectation of theta hat minus theta naught. Theta is mean for us in this exercise and theta naught is mu, and therefore we get this. So to give you an idea, pictorial idea of this, so let us say the mu is here, the truth is fixed, and our estimates are all over the place, I mean not all over the place, but to the left and right of mu. Each crosshair mark is an estimate from a data record. We talked about this in the example, and we also simulated when we use the command replicate. In each iteration of the replicate, it is actually generating a data record. From each data record you have an estimate which is denoted by the crosshair mark here. And what this result says is that the average of all such estimates coincides with the truth. If it does not, then you have a biased estimator. As a simple example, suppose in place of 1 over n, I had used this estimator x bar, let us call this x bar tilde as a different estimator with 1 over let us say n minus 1. Then here clearly expectation of x bar is n over n minus 1 mu, which means the average of all such readings would fall to the right of mu. So if you think of the origin being here, essentially right or left we are not so much worried about it, does not coincide with mu, and in this case, sorry, it is not x bar but x bar tilde. In this case x bar tilde is a biased estimator, which means there is a systematic difference between x bar tilde and mu. Again you should keep telling this to yourself that every estimate, that is estimate computed from every data record, will always be in error. That there is no denial, it is a fact to acknowledge. What is important is to see if the average of all such errors will be 0, so that the expectation of x bar coincides with mu. So we have now computed the mean of x bar, correct, and that turns out to be mu. And now we can also use this result to derive the variance of x bar. Alright, so let us now derive the expression for the variance. Now I just noticed that there was a small mistake, I am sure you would have noticed by now and would be eager to correct me. So here you go, I stand corrected. We have here 2 times alpha 1 alpha 2 times covariance. Anyway, this result would not change eventually whenever the covariance is 0. Alright, so now let us actually use this result to derive the variance of x bar. We have not yet come to the distribution of x bar. As I said earlier, the expressions for the mean and variance do not really have anything to do with the distribution of xi's. So this result, that is on the unbiasedness, holds good for any situation, that is regardless of whether this holds or not. Now we are interested in variance of x bar. Remember now that we are looking at 2 random variables, one is x corresponding to your population, the variable of interest, and other is the x bar. So do not get confused between these two. It is a common thing to be confused between x and x bar, but with some practice you can get over that confusion. So sigma square x bar is what we want, and we can straight away use this result. We know that alpha 1 or any alpha I is 1 over n, and because each xi falls out of the same distribution, I can therefore say that it is sigma 1 over n square. That is, if I extend this result to the n random variable case, I would have 1 over n square times sigma square, and that gets me sigma square over m. This is a very useful result in many different ways. Of course, we have derived this result assuming, now at this point we have assumed that each xi is uncorrelated with the other. We do not even have to assume independence, but if the observations have fallen out of a random sample, then anyway they are independent and then they are uncorrelated. So that is anyway true. So the only assumption that we have made here in deriving this is that xi's are independent. We have still not made use of the Gaussian distribution at all, whereas here we have not made use of any kind of assumption apart from the fact that xi has a mean mu, that is all. Now this is a very important result in many different ways. Remember, we talked about precision of an estimate, which tells me or the variability of an estimate, which tells me how x bar varies from data record to another data record. And larger the variability, worse is the situation, because the estimate that I compute from one data record is not truly reliable. So what we want to achieve is a high precision, which means I want the sigma square x bar or sigma square theta hat, you may say, to be as low as possible. This is good. So when can I achieve a very low variability in the parameter estimate or high precision in the parameter estimate? Let us look at what affects sigma square x bar. One is sigma square, which is the variability in the population. So this is the variability in the process itself. Let us use the term process. Variability in the process, random process, which very rarely we have a control over. Of course, if it is a manufacturing process, if it is a man-made process, then by design I can actually try to minimize this, but I can never take this to 0. If it is a natural process such as an atmospheric phenomenon and so on, then I do not have any control. Therefore, this is something we will assume that is fixed for an experiment, because once the process is designed or already naturally in place, sigma square is fixed. So the only factor that I have in control to control the precision is n. Of course, this is not necessarily part of hypothesis testing, but it is something very important to know. Eventually, this number of observations does play a role in the goodness of the hypothesis test. So you can therefore think that this is a very relevant discussion. As I increase the number of observations to infinity, infinity is a mathematical term, in engineering terms very large, let us say 1,000,000 observations, then sigma square anyway is finite, so you can expect sigma square x bar to go to 0. So the result that we have is, in the limit as n goes to infinity, sigma square x bar goes to 0, which is a very good result, which means that as I collect more and more samples, the precision of the estimate improves, and finally at some point sigma square x bar hits 0 or an extremely low value. And if you recall, when we discussed the notion of variance, we said when a variable, when a random variable is such that its variance goes to 0 or its variance is 0, then it loses its randomness and becomes a deterministic variable, which means now it will reach a fixed value, that is x bar will reach a fixed value. And what is that fixed value? Mu. So what this tells us is that as n goes to infinity, the estimate converges to the truth, and when this happens we say it is a consistent estimator. And of course now we can ask another question, which is typically asked in estimation, whether this is the lowest variability that I can achieve. The positive square root of this is called the standard error, which will be useful to us in confidence interval construction. So the standard error for x bar under these assumptions is sigma over root n. Again, you have to ask yourself what assumptions we have made. We have made an important assumption, which is that xi's are uncorrelated, or maybe a stronger assumption, xi's are independent. Therefore, if xi's are not independent, which means if you have taken a sample where the observations are biased, then this and all the discussion that we just had need not apply. Okay. Now, the question that we asked earlier just now is whether this is this standard error that we have achieved in X. We call it a standard error. You should actually make note of this standard prefix there, because this is not the error in x bar. If this was the error in x bar, I would simply go and add it to x bar and get the truth. All right. So this is a standard, which means it's an average error in x bar. Whether this is the lowest possible error that I can achieve in the estimate of mu. Mu is the truth that I am trying to estimate. Is there any other way of estimating mean which can give me error lower than this? Although we won't prove anything, it is a widely known result that when the observations are uncorrelated, this is actually the so-called minimum variance estimator. X bar is a minimum variance estimator of mean, or in other words, the most efficient estimator. There is no other estimator that can be more efficient than this, which means if you were to use sample median, it would have a larger error than sample mean. That is a very interesting thing to know, because when you are computing hypothesis tests, when you are conducting hypothesis tests, we have to choose a test statistic. That's one of the key steps, if you recall, in the general procedure. So when it comes to choosing a test statistics, there are several options, of which we choose an estimator that is efficient. That means it has the lowest error and it is unbiased. These are very important things, because if I choose a biased statistic to conduct a hypothesis test, the outcome of the hypothesis test is also going to be biased. So it's important that when you choose a test statistic for hypothesis testing, you are sure that under the circumstances and the assumptions that you have made for the process, you are choosing an unbiased estimator, and if possibly efficient estimator. Now here in this case, we were able to verify very quickly that it is an unbiased estimator, and of course we have not proved that it is the most efficient, but even showing that it's fairly easy. In a general scenario, it may not be so easy, for example, to know if you are working with the fully efficient or the most efficient estimator. And likewise, it may be also not so easy to determine whether the test statistic that you are using is actually unbiased or biased, but you can look up the literature and determine whether somebody has studied the biased nature of it. Fortunately for us, the kind of problems that we are going to look at involves test statistics such as sample mean, sample variance and so on. They are all unbiased, of course under some conditions. Nothing is universally unbiased. So this is the story here. Now coming back to the distribution. Now we go back to asking where does xi come from? What is the maternal place for the random variable? The maternal place happens to be Gaussian. And under these assumptions, this result that we have just seen on the screen tells me that x bar follows a Gaussian distribution. So that's it. So now I can put together everything and write that x bar follows a Gaussian distribution with mean being the same as the process, but the variance being sigma square over n. This is a fantastic result that we have. Now we can use this to conduct hypothesis test, and we will also show that this is very useful in constructing confidence regions. Now often this result is written in a standard form, so that we say x bar, this is, it's not so appropriate to write this, will not, the reason being when n goes to infinity, the variance goes to 0 and x bar no longer has any randomness in it. and therefore we cannot talk of any distribution. So there is a degenerate case there, situation there. On the other hand, if I consider a standardized random variable constructed from x bar, which we normally call denote by z, this remains a random variable even of course when n goes to infinity, and this we say follows a standard Gaussian distribution with mean 0 and variance 1. That is why in many textbooks you see this distribution being given more often than this. Of course, for finite n this is all fine, it is only for infinite n that does not make much sense, but this is the birthplace of this statement, alright. So which means now what we have understood is when the observations are obtained randomly and they fall out of a Gaussian distribution, the sample mean first of all is an unbiased estimator, is the most efficient estimator of the mean and follows a Gaussian distribution. Excellent. So this is what we want. Now typically this is a procedure that we follow for every parameter estimate, but the question is it going to be that easy to determine? Even in the sample mean case, suppose this was not true, then what about the distribution of x bar? This has got nothing to do with this here, the distribution of x. The central limit theorem comes to the rescue and says that for large n, x bar follows a Gaussian distribution, but we may not have such privileges for other kinds of estimators, because what we have here is a linear estimator. This is said to be a linear estimator because as you can see, the estimate which is x bar is a linear combination or a linear function of the observations. Linearity has got nothing to do with the equal weightage. I could have given different weights also. Linearity has got to do whether the right hand side is a linear function, and we all know the definition of linear functions. So for linear estimators, typically it is easy to derive the distributions, especially using central limit theorem, but for nonlinear estimators it becomes difficult because there is no theorem per se to straight away help you, and even deriving some expressions analytically. Only for the variance part it is a bit easy because we have a random variable which follows a chi-square distribution and so on. That is something that we will make use of, but in general when you are looking at a complicated estimator which is a nonlinear function of the observations, becomes difficult to determine the distribution analytically, that is by hand. So then what is the natural recourse? The natural recourse is to turn to Monte Carlo simulations, something that we did in the example. Remember, we went through an illustrative example where we observed that sample mean follows a Gaussian distribution. Here we have derived it theoretically. So in a general scenario we may have to turn to Monte Carlo simulations where we repeatedly generate the data and then determine different values of the estimate theta hat, and then plot a histogram of it, from where we try to fit a distribution. What if I cannot perform simulations? What if it is an experiment? How do I determine the distribution of a statistic for an estimator that is a complicated function of the experimental data? That is something which I cannot simulate. Then unfortunately we cannot perform repeated experiments, infinite number of experiments. That would be a near impossible task. What is therefore done instead is a technique that is used called bootstrapping, which again falls within the gamut of Monte Carlo methods, and we will not perhaps talk about it now. If I get an opportunity towards the end of the course, I will talk about bootstrapping, which will allow us to determine the distribution of an estimate that I cannot determine analytically, but I can determine using a single record of data. That is very interesting, isn't it? So let us wait and see for that. Now let us get back to the more comfortable world of deriving distributions analytically for the statistics of interest. So we now learned how this single result is so useful in deriving the distribution of sample mean. What are the other results that we have? The second result that we have is the distribution on sum of squares of standardized Gaussian variables. So as the expression shows here, what I am doing here is I am standardizing xi and then squaring it. In this case, the standardization, always the standardization of a random variable would mean that random variable minus mean of that random variable divided by the standard deviation. So here earlier we standardized x bar where whose mean was mu and standard deviation was sigma or root n. Here we are standardizing xi. Now when I take such standardized variables and square them and then sum them up, the resulting random variable that is born out of this operation follows what is known as a chi-square distribution. This is something that we have learnt earlier when we went through some standard distributions. We defined chi-square variable as a sum of standardized squared Gaussian variables, and we then there we said that the random variable follows a chi-square distribution with n degrees of freedom. This degrees of freedom has got to do, you can say loosely, with the sources of variability. All right, how many independent sources of variability do you have? So here we have n terms in the summation and each term is contributing to the variance of y, and therefore we say assuming that all of them have, are independent of each other, xi's are independent of each other, and which is true when xi the x1 to xn constitutes a random sample. So in that case each term has a unique contribution to the variance of y, and since we have n such terms we say that it has n degrees of freedom. Quite a people have difficulty in understanding the degrees of freedom in statistics. Degrees of freedom is a term that you will see in linear algebra, in engineering. It's a very common term that's used. Now where do we use this result? Of course we use this result in the derivation of sampling distribution of variance, and I will talk about it later on. When we look at sampling distribution of variance, we will see how this result comes handy. And the other result that we may use is when I add up n chi-square distributed random variables, then the resulting variable also has a chi-square distribution. So if xi falls out of a chi-square distribution with ri degrees of freedom. So here it is different. So what I am doing is I am actually computing the sum of n chi-square distributed random variables. Until now we have been assuming normally distributed random variables. When I do that, the random variable that is born out of this operation is also a chi-square distribution with r degrees of freedom, where the r degrees of freedom is simply the sum of the ri or the sum of the degrees of freedom of the respective variables. Again here the important requirement is that each xi is independent. Only then the degrees of freedom add up. A lot of times this independence affects the degrees of freedom more and less on the distribution. So for example, if you go back to the discussion on x bar, we have assumed that xi is independent and so on. Suppose xi were not independent, would that affect the expectation of x bar, average of x bar? No, we have seen that that assumption is not required. Does it affect the variance of x bar? Well, it does, because the expression for computing the variance changes because the covariance, cross covariance terms kick in, and then the variance takes a different expression. What about the distribution? Is the distribution affected? Typically not so much. The distribution may still remain Gaussian, but the variance would change. At least for this we are talking for the large n case. Here as well, when you add up chi-square distributed random variables, we may ask how does independence affect the distribution of y and so on. We cannot answer definitively because we need some theory, but intuitively speaking, the first factor that the independence or lack of independence would affect is on the degrees of freedom. Now of course what I leave to you as a simple exercise is to verify even this result for the independent case through simulations R. Again using the same thing, you can actually, instead of R norm, you use R chi-square, RCHISQ, and add up n such variables and see what distribution it follows. I will give you a sample and then you can take it from there. So what we shall do is we say hist, again use the same idea, repeat the experiment 1000 times. What do we do here? Sum up, let us say 10 random variables that are all coming out of the same distribution, which is a chi-square distribution. In the result that I have given, we have assumed each random variable comes out of a chi-square with different degrees of freedom. Here we will assume that they are all coming from chi-square with the same degrees of freedom, just to simplify things. So now I have to specify the degrees of freedom, as also nicely the help shows in RStudio. So let us say that each random variable comes from a chi-square distribution with 5 degrees of freedom. I am summing up those 10 observations and I am going to repeat this, and then I am going to plot a histogram so that I get an idea of the density. Sorry. Okay. Right. So you can actually see that in this case the there is a certain asymmetry. It looks like a bit of Gaussian, but it is not. It is actually a bit chi-square. In fact, what we can do is we can even reduce the number of variables that I am adding up. Let us say 4 such variables. Now you can see it is tending towards a chi-square. So on the other hand, if I actually add up many such random variables which follow a chi-square distribution, let us say 100, you can see now the distribution is tending towards a Gaussian. So is this a violation of what we have seen? No, because because a chi-square distribution with large degrees of freedom will tend to a Gaussian distribution, take the shape of a Gaussian distribution. So the result is not violated. The result is still that it is chi-square distribution, but with a large number of things that we are adding up. So what is the degrees of freedom for this case? That is, what we are doing is we are adding up 100 variables, each with 5 degrees of freedom, and they are independent because R chi-square samples randomly. So if you look at the result, it says the degrees of freedom for y is the sum of the degrees of freedom of the respective random variables. We have added up 100 of them. 100 times 500 degrees of freedom is way too high for the chi-square to remain a chi-square. It becomes Gaussian, it takes the shape of a Gaussian distribution just maybe by about 30, at around 30 degrees of freedom itself. So even when we used 10 random variables to add up, each with 5 degrees of freedom, the resulting degrees of freedom for y was 50. So truly to see a chi-square distribution for y, we should either reduce the number of variables that we are adding up or reduce the degrees of freedom for each of them. So we can do one of these. Here of course we reduce the number of observations to 4. What we can do is we can say add up 10, but each with maybe 1 degree of freedom. So here you can clearly see that it is a chi-square distribution, and in fact the exercise for you is to check if this is something that you get as a chi-square distribution with 10 degrees of freedom, because that is what the theory says. We are adding up 10 chi-square distributed random variables, independent random variables, each with 1 degree of freedom. You can either generate the density curve for a chi-square distributed random variable with 10 degrees of freedom, or you can use density fitting tools. In R there are wonderful density fitting tools to determine what is the best chi-square distribution fit for this, and you may find that the answer is 10 degrees of freedom. So it is a very nice simple exercise that you can go through. Very good. So you can see simulations really help us a lot in understanding and sometimes corroborating the theory. But of course theory always remains powerful.